All right. Thank you, first of all, for having me. I'm very happy that I can share some of my work or the work of our group here or at TUM in Munich. So we are the Professorship of Digital Fabrication, very similar to what is happening here, under the lead of Katrin Dörfler. We have grown quite a lot since we started in 2019, and we have been using COMPAS since the very beginning, as Katrin took it with her from here. I will talk a little bit more about what we now do. So as you saw already, there's a whole list of programs that people can use. We, of course, use Rhino and Grasshopper very much, and we started now with the Isaac Sim from NVIDIA as well. And then we have the middleware, which we have COMPAS with a couple of different packages that we use a lot. And then the backends, which are, for instance, Robot Studio, we use a lot of ROS, but also packaged in Docker, for instance, and for PyBullet for some motion planning. So the libraries that we have ourselves, I listed them here for you. This is just a selection of them. And we have some different ones that do the storing of geometric data or fabrication data or semantic data, which are in these AM and assembly models. And then we have a fabrication manager, which kind of controls the actions in between different actors. And lastly, what I will talk about mostly today is the mobile robot library, which contains of a couple of different fields. So I segmented them here for you nicely. So we have also a core packages. So these are just the essential tools that you need for the mobile robot. Then we have the planning and the localization. And after that comes the control. So in the core package, we have some very simple features, but essential nonetheless, which are the setting of the base coordinate frame as we are moving the robot around. We have the transformations for all of those points, and we have also the callback, so we can always know the exact position of the robot and the different components of the robot. Then there's the planning, which focuses more on reachability. So where the robot is, can we actually manipulate a specific object in the environment? That we can then also relate to where the base is. We can plan the base motion, and we have a semi-constrained path planning for the end effector, which helps us in a tight spot. Then localization is very much key. As we are moving the robot around all the time, we have to accurately know where it is to manipulate an object in our space. And lastly, there's the control commands. So here I try to list a little bit more detail the dependencies and the backends that we use in this specific package, which are COMPAS, COMPAS Robots, COMPAS Fab, ROSLibPine, Open3D. A lot of it's inherited from COMPAS and to aim to extend the functionality that is already there. And some of it is also just used. Currently, our robot is based in ROS Noetic, so that's ROS 1. There will be a migration soon to ROS 2, and we're very excited to see how we can actually implement that as well. And then, as I mentioned before, we have the PyBullet for motion planning itself. All right, so the mobile robot class, when the robot is started, you can see here at T0, the robot is at a specific position which also coincides with the base frame of ROS. So whenever the robot starts, it says it's in world 0. Then when we start moving it around, it starts to navigate from that position. However, this frame is not always the same as the one that we have in Rhino, so we also have to have that transformation listed in there. Then we have, as I mentioned before, the callbacks for different joints. So the manipulator we have for our robot, as well as a linear axis, and then the wheel configuration. Now, where do we actually want to place the robot is a very important question. And for that, there is this reachability evaluation that is now also listed in COMPAS, I saw. However, this is an implementation directly from ROS. So here we're just listening to a topic after a reachability map has been generated by the Rulo ROS package. And this we can then visualize and place in Grasshopper. And what we actually want to do with this is, as you can see, we have an object somewhere in relation to the robot. And we can create a point cloud out of that object, for instance, by just populating a number of points. We can then attribute the reachability points to that object. And from that, we can determine how good that position is for the robot to actually manipulate from. So when we then take that a step further and we basically then attribute the mean value of all of those points to the specific position of the robot, then you can see this little blue dot there kind of represents how good that position is for that specific object. Now we can do that for a whole bunch of different points around, and we can then find which one is the ideal location. Here, this is just some random points, but we can, of course, also do that for an entire grid and create a whole map. So mapping out the space around the robot to find where we can place it most optimally. Now on the left side, you see that there is no differentiation in the reach when the actually robot would stand inside of the object. So this is of course something we have to correct for. It doesn't account for collisions. So we apply a closeness penalty, so literally a penalty for distance. And with that, you can see that the field shifts, and the blue points here are the best points. And you see that where the robot is standing now intentionally is the optimal position coming from this search. Now, of course, this is a rectangle and it's very simple, and it's of course going to sit on one of the sides. If your geometries get more complex, then it's not always that obvious. So this is a very helpful tool. Which we also use. So for instance, here we have a wall that we segmented in different components. As we are printing this wall in different pieces, we are always moving, then we are printing, then we're moving again. So we're never printing and driving at the same time in this circumstance. And for this, we also evaluated for all of these segments where we would place the robot, and we would therefore get a security that we can always reach all the points of this segment, for instance. Now, moving on to planning. So you can think of base motion planning as just a start and an end point. Now, of course, that can become a little more complicated. So we have a curve. To make it simpler for the robot, we can divide it into circular segments and linear segments. And this is called a Dubin's curve. And with our robot, since all of the four wheels rotate individually, it uses a dual Ackermann steering principle, which basically means that the inner wheels have a different radius than the outer wheels, and it can follow the curve in this way. And this is an implementation that we have recently also made for the Isaac Sim, so we can actually simulate this motion before going anywhere near the robot. Then the manipulator motion planning is a semi-constrained path planning. So here we have to make sure that the robot can print in between these two beams without hitting it. This is only possible when we actually rotate the nozzle around. So we have a free rotation axis around the z-axis. And in this case, we have a list of configurations that are generated for each point with a free rotation around the z. It's basically doing inverse kinematics for all these points and finding the shortest path between them. So a kind of a least cost optimization. With that, I will move on to the localization method. So this is also something that we have now implemented. You can differentiate between a couple of different categories again. So we have environment relative localization or object relative localization. And especially for this latter one, we have to commonly do a point registration method. So environment relative is rather we take a map of the environment with a LiDAR, for instance, that is in our case mounted on the front of our robot. That creates this kind of point cloud that you see at the bottom, and the robot can kind of match these the sensor data with this map, which is called SLAM. And from that, we get a robot location. This, however, is not as accurate as we need it for printing, which is where our object relative localization comes into play. What we do here is we take information from the odometry topics or the the transform topics, or in some cases, the sensor topics into our design environment again to manipulate it there more comfortably. For localization, we have 3 different methods that we are using. Generally, simply point measurements, where we put the robot in one position. We get the different joint values of the robot. We therefore know where that point is in relation to the robot. The same we can do for marker tracking. So we have a camera actually finding the marker location, or we do point cloud capture, which you can see on the little video on the bottom, where we have a line scanner that's moving along our, in this case, printed geometry to record the surface. Now, in any of these circumstances, we have points or a point cloud that we have to find the location of in the virtual space. So for that, we have a global point registration method that we use and a local point registration. So the first one doesn't require any guesswork. It is trying to fit, in this case, the blue cloud here that you see on the left to the red one. And it uses a random sample consensus method to find a good fit for that. However, it's never going to be very, very accurate because it's meant as a global point registration. And as a result, we have a second one, which is maybe one that you're more familiar with, is the ICP, the iterative closest point. And this makes a fine adjustment. That's why you can see these 2 frames at the bottom there. So from this, we get our base location. Then our control. So we have, for quasi-stationary approaches, without this unified controller, we have these motion commands like the linear axis, the base movement, or the arm motion. And these routines or actions, they're being controlled by this event-based fabrication manager that we use. Ongoing for us is the holistic motion control. This is something that we're working on in this current phase of our research. Nevertheless, I will show you a selection of some projects that we have now done with this mobile robot, with these tools that I've mentioned before. The first one of this is cooperative extrusion. So here we have 2 robots that are localized opposite from each other, printing at the same time a earthen mixture, which is simultaneously filled with concrete. So it's a bit inspired by projects like Eggshell or clay formworks or any kind of formwork printing project. And here the robots are waiting for each other at every point to make sure that we're, of course, not hitting each other, which was a very interesting project to work on. And also something that we can only do with multiple robots as we are printing around a reinforcement gauge. Another thing we can do with mobile robots is we can also go on-site. So what we can also do is we can actually scan existing building parts, and we can then analyze that, and we can make something that fits perfectly inside of it. This is here a brick wall that we have scanned with this laser scanner, this line scanner that you saw before. And we can fit an object there in there perfectly, and we can fill it up using 3D printing. And then another project, which I already showed a little bit before, is this wall printing project. Sorry. So here we move the robot, then we scan the part, which has been scanned before. So whenever I print a segment, we scan it, then we move, then we scan again, and then we have something to compare it to. And after that matching, we can see we can get a pretty good match for the robot location, and we can create a near seamless printing on top of a previous segment. So all of these segments are localized relative to one another. There's, in this case, no global tracking on it. And then last project, which is maybe very familiar to some of you, Daniela Mitterberger, Eleni Alexi, Joseph Kenny, and Gonzalo Casas all worked on this as well, together with our group, with Lydia Tarasova and Catherine and Begum here, where we use an XR app and marker tracking So we have the mobile robot that is localized using the marker tracking. Then we have the AR app that then chooses whether it's a human action or a robot action, and that way collaboratively build this tree structure together with these robots. Then as a short outlook, I am currently in the last phases of my PhD, and I'm very much looking forward to also taking what we have developed and giving it out to more people to use, and trying to see if maybe we can make a COMPAS mobile robots or an extension of the COMPAS Fab library to include this kind of mobile robots features. And then what we further have is this fabrication design and modeling and this fabrication manager that we also would like to collaborate with you on. That's the last of my presentation. I'm very happy that you gave me the chance to speak here, and I'm looking forward to seeing what else people have to say. Thank you.